Okay, hello one and all. So, firstly, I want to thank my department to give me this opportunity, especially I want to thank Dr. Elizabeth and Dr. Ham for this chance. Well, my talk will be about Thinshell wormholes. Almost all of the physicists, theoretical physicists, have some ideas about wormholes. Also, ordinary people have some ideas about wormholes. They can visualize wormholes somehow. We've seen wormholes many times in the movies and in sci-fi movies, in the books. There are many artworks. If you Google the name wormhole. But Thinshell wormholes, on the other hand, are not so well known. So today I decided to talk about Thinshell wormholes. This is actually what I'm currently working on, and this will be the title of my thesis, asymmetric Thinshell wormholes particularly, but they are kind of wormholes. So my speak will be so general for everybody to get some ideas, but at the end I'll be, in the last 5 minutes maybe, I'll be a little bit more technical. So I'm going to speak about wormholes first. Very briefly, then I will introduce Thinshell wormholes, or what I refer to as TSWs in short, and then I will talk about asymmetric Thinshell wormholes. Actually, I had planned to talk about TSWs in new massive gravity, which was one of the articles that we had written a couple of months ago, but I think I have to ignore this part at the end due to time limitation. So first, I think this doesn't, oh maybe, yes, Dr. Ozai.
Yes. No, I put it. Okay,
Oh yes, it's here. Sorry, my mistake. Okay, so a wormhole basically is a structure which connects two distant parts of two space-times. Actually, we have an intra-wormhole if the wormhole connects two parts of a single space-time, and these two distinct points in the space-time can be two spatial points, some millimeters away from each other, or millions or billions of light years away from each other, or it can be serve as a time machine to connect two points different in times in a single space-time. Also, if you talk about extra wormholes, they can connect two points from two different space-times. So generally they are visualized, well, geometrically. If we draw the embedding diagram of wormhole, it can be visualized as a tunnel which connects two distinct points, as I mentioned. But also, if you, as I said, if you check the artworks of wormholes on Google, also you see that they have some tunnel structures. The question is, are they really traversable or not? They appeared the first time as solutions to the field equations of Einstein field equations. The most well-known wormhole was Schwarz wormhole, or Einstein-Rosen bridge, but it turned out that this type of wormholes were not traversable, meaning that they too quickly closed before a traveler or a particle even can pass through. So wormholes were not traversable until the work by Morse and Thorne at 1988, where they described a structure which has actually a solution to the Einstein field equation, which had a tunnel shaped structure, and it represented a wormhole. So for the first time, they introduced traversable wormholes, and very soon after their work, Morrison actually wormholes became a hot subject in general relativity again. So this is again an artwork which shows a wormhole which connects two different points of a single space-time. They can be seen as some shortcuts to go from one point to another. It's like you have a wall, and if you want to go to the other side of the wall, you have to go and take a turn, but a wormhole is like a secret door in the wall that you can just open and pass through the doorway. So now Thinshell wormholes, as I said, in 1988, for the first time traversable wormholes were introduced. 1 year after that, in 1989, Matt Visser, the New Zealander scientist, introduced Thinshell wormholes. And Thinshell wormholes, unlike wormholes, are not exactly or directly, let's say, the solutions to Einstein field equations, but they are somehow fabricated. The way that a Thinshell wormhole can be constructed is more like what I'm going to show here. You have a space-time, it's a completed space-time. It can be any space-time, almost any space-time can be used or can be applied to construct a Thinshell wormhole. Then you excise out some part of it. All the singularities and event horizons, everything is in this part. So you just take them out, and you do the same thing with another copy of this space-time, and then you bring them together, just like that. Okay? So imagine a bug or an ant moving on this surface, on this page, and suddenly when it reaches to this point, it finds itself on the other side of this paper, which is actually another universe. So a Thinshell wormhole is particularly designed to connect two universes to each other. As I said, the two copies were the same at the beginning of the history of Thinshell wormholes, exactly two copies of the same. If you have Schwarzschild, let's say, I'm going to refer to Schwarzschild because Schwarzschild spacetime is the best known solution of field equations. So if you have two Schwarzschild spacetimes, then both of them will have the same mass. Okay? This is of course a two-dimensional illustration of Thinshell wormholes. Three-dimensionally, they can be visualized as a sphere, and when you get close to the sphere, it's not dark, it's not solid, you cannot see any surface, but you somehow see a distorted image of the other universe that you're about to enter. So there are some advantages for these TSWs. The advantage, I think I pointed out at the first one, is that you can construct Thinshell wormholes using any kind of spacetimes. Wormholes themselves have structures, and they are solutions of specific solutions of the Einstein field equation, but Thinshell wormholes can be constructed almost from any kind of other solutions which are not wormholes. The problem with the wormholes, the general problem, the most important problem with the wormholes is that they need exotic matter to stabilize them. My colleague Dr. Ali yesterday spoke about exotic matter in details. They have negative energy or negative mass, so that's why we call them exotic. But this exotic matter also exists for Thinshell wormholes, but the difference between exotic matter in wormhole and Thinshell wormhole is that in wormholes, the exotic matter is distributed all over the structure of the wormhole, and sometimes it can extend over the whole space-time. But in case of Thinshell wormholes, the exotic matter is only on this boundary or this junction of the two spacetimes. So the exotic matter is confined inside, on this circle here in this case, or on that sphere in the three-dimensional or four-dimensional world. There are, of course, some certain junction conditions, meaning that you cannot just randomly, again, this is another illustration, very simple stuff. You have one universe, another universe, then you cut some part of them, and then you join them. So you cannot do this randomly. Of course, they should have the same radius at this point. They must be connected smoothly, and for the spacetimes to be consistent at that point. And then they have to be physically meaningful. I mean, the exotic matter and everything that we know about the physics should be consistent at the joint hypersurface. I will refer to these junction conditions later. Thinshell wormholes, as I said, cannot solve the problem of the exotic matter, but the exotic matter is confined now. The other advantage of Thinshell wormholes is that there's a method to assess or analyze their stability, which is called the linear stability method, developed by Poisson and Visser in mid-1990s. And the junction conditions, actually Visser didn't have to deal with the problem of junction conditions, because the junction conditions, the formalism of junction conditions at the time was already developed by Danial in Israel some decades ago, when he actually developed the theory of Thinshell wormholes. So the next part is asymmetric Thinshell wormholes. As you can see, until 1 year ago, 1.5 years ago, that we started to work on asymmetric Thinshell wormholes, there was no scientific article that used two different spacetimes. By different, I mean all of them had some mirror symmetry. Okay, if you have one Schwarzschild spacetime, the other spacetime is the same Schwarzschild spacetime with the same mass. But if Thinshell wormholes are about to connect two universes of two different universes, so let them connect two real different universes. So this is the part that becomes a little bit more technical. We said that, let's imagine that we have two static universes with diagonal metric. This is what we have. ds is just minus f dt squared 1 by f drs squared plus the angular part. And then f can be anything. It can be Schwarzschild or Weiser-Nordstrom or anything else. Then these are the junction conditions. The first junction condition is very simple to understand. It just says that when you approach the throat, the two metrics should become the same. Okay, that's the first junction condition. And the second one actually puts a discontinuity on the second fundamental form, which is the extrinsic curvature, and it is given in this form. KAB is here we have the extrinsic, the mixed extrinsic curvature tensor, and this is its trace, and this is the energy momentum tensor of the exotic matter on the throat. So I'm not going to go through these. I just mentioned this. So here, by actually writing the second junction condition, we can write an equation of this form with this effective potential. F1 and F2 are referred to the metric functions of the two spacetimes. So here, this term is a new term that was not there before, because F1 and F2 were the same, so the subtraction would give 0, but now we have them in the formulation. And then this effective potential in a static form can be written in that form. We can Taylor expanded about a radius, an equilibrium radius, which we suppose that exists. Then we see if the second derivative of the potential with respect to the radius is positive, then it shows that the Thinshell wormholes is stable. So I just cut to the results, to the conclusion. This is what we actually did it for many spacetimes. We connected Schwarzschild to Schwarzschild with different masses, which is this case, m on one side and m times 1 plus epsilon on the other side. We connected Schwarzschild to flat spacetime, Reisen-Nordström to Schwarzschild, two spacetimes of different natures. But this is the result we got. Just to show you what are these, this on the horizontal axis we have the radial coordinate, and on the vertical axis we have the speed or the squared of speed of sound in the exotic matter on the boundary, on the junction. So you can see this bowl-like shape or U-shaped branch here. Inside this, it's like that. And inside this U-branch figure, you see here the Thinshell is stable. So we draw these 4 pictures for different values of epsilon, and epsilon, as I said, can be referred to as asymmetry agent or asymmetry factor, something like that. Also here, underneath this zero-seeking branch, we also have a stable TSW. So here and there. And then you can see that how asymmetry or how a degree of asymmetry can change the shape. The general, the universal shape is almost the same, but they move and they, some parts they squeeze and some parts they actually they are expanded. We did this in spherical spacetimes and also cylindrical spacetimes. We were more conclusive for spherical spacetimes because it was observed that exactly for all of the spacetimes that we tried, the symmetric case was the most stable case, but not for cylindrical spacetime. We were not so conclusive for those. And I think that's it. I'm not going to go through new massive gravity and other things. Just a very quick thing for new massive gravity. You saw the junction conditions for general relativity, Dorn-was-Wright junction conditions. The smoothness of first fundamental form and then a jump in the second fundamental form. But now look at the junction conditions for new massive gravity. They're so complicated. The junction conditions in general relativity were developed in 1966, but these were developed in 2014 or 15, something like that. So complicated, much more complicated. And I think that's it. Yes, we have 2 published. We've been doing this for the last 1.5 year, less than 1.5 year. We have 2 published papers and we have 3 other papers under review, right? Thank you so much for listening.
Any question? One more.
You know, when I was young, I watched a cartoon called Doraemon. I don't know, did you see that?
No, I'm afraid.
Doraemon, they can pull a door from his back, and you can enter the door whenever you want. A signature with his friend let him watch Doraemon.
Yeah.
Did you think that's possible?
Well, actually, no, I haven't seen that movie or TV series, but you know, in most of the movies or TV series that we see, we have wormholes as the passages through other universes and stuff. But there's a movie that I can remember, Stargate, if you have watched it, or the TV series Stranger Things, that they pass through, like, it's just a layer and then they go to the upside down, which is another universe, parallel to our universe. So these are the only 2 movies or TV series that I can remember which had somehow Thinshell wormholes included. In that.
If any information can enter home.
Any?
Information.
I really don't know. I really don't know if the information, if there is any information stored on the Thinshell wormhole itself or not, or if the information can easily transfer from one universe to the universe. My knowledge is not that vast.
Thank you very much.
You're welcome.